Hello everyone. Next, we'll go for the another topic, that is the boiling. Boiling means we know that one exactly opposite of the condensation. The condensation means there is the change of phase from vapor to the liquid, but in the boiling means the phase changing from liquid to the vapor. Here can see change. You can see that the phase changing from liquid to the vapor. That one you're going to call as an boiling process. When you are supplying the heat, the liquid is going to be converted into the vapor. In boiling modes, there are different boiling modes will be there. That is what pool boiling, forced conversion boiling, subcooled boiling, and saturated boiling. Likewise, the four different boiling modes will be there. In this one, we are going to discussing about the pool boiling. Pool boiling. This is also asked in most of the time in the examination related to the theory part and notes already given. I briefly explain about what is meant by the pool boiling regimes. This one is also asked for a 4 marks or a 6 marks in the examination. These things also are given. But in the most of the time, this pool boiling regimes is commonly asked in the examination. Very important for the examination point of view. Pool boiling regimes. The name itself indicates the pool means a beaker containing a full of water. That one you're going to call as a pool. In that one, a heater will be there. This is the heater. For this one, the electrical heater, the current voltage means and amps will be passed to the electric heater to get because of resistance they will get heated. Okay. This heater will helps to boil this what the water is there in this beaker. This one you're going to call as the pool boiling regimes. Okay. Pool means a pool, a beaker containing a full of water. In that one, a stationary electrical heater will be there. Electrical heater. That electrical heater will be go on heating the liquid is there in the beaker. Okay. Now first in this one, for this one, this is the graph actually we obtained. When you are go on supplying the temperature, means when you go on giving the current to this one, the resistance will be increases, automatically the temperature will be increases. From here to means temperature difference, the excess temperature difference 1 to 1000, for this one the graphs is open. Here you can see that Ts minus Tsat. Ts means surface temperature of this heater and Tsat is the saturation temperature of this fluid liquid. Here now you consider this is the water, and the pressure is 1 atmosphere pressure. Then Tsat is how much? 100 degrees centigrade. Here 1 represent means the Ts minus Tsat is what? 1. Suppose this is the 100, Ts minus Tsat is equals to 1 means then surface temperature become 101. Suppose Ts minus Tsat is 30, Ts minus Tsat is equals to 30 means Ts minus Tsat is equals to 30. Tsat is how much? 100. So Ts is equals to surface temperature is equals to 130 degree centigrade or 140 degree centigrade, like that. Okay, this is the excess temperature difference. Excess temperature means Ts minus Tsat. Wall temperature minus saturation temperature of the liquid at that pressure, corresponding pressure. Now the difference is 1, and for the 5, for 30 or 120, the graph will be changed like that. Okay, in this one there are in the pool boiling regimes there are different zones. The first zone you're going to call as the free convection zone, and for second and third you're going to call as the nucleate boiling. The first one is free convection boiling, nucleate boiling. Next, fourth going to call as the transition boiling. Next, stable film, radiation and film boiling. First you come to this one. When current comes here, the resistance will be increases, the temperature will be very less compared to the saturation temperature of the water. In that time what happens? Free convection will be happens, natural convection will be happens. Here you can see that very small surface area, that surface area zoom to this one here, the zoomed area of very small surface over the electrical heater. The first one is the natural convection. What the surface is get heated, that will be given to the the fluid by because of the natural free convection, because of the density difference, because of the buoyancy effect, the heat transfer will be takes place from surface to the fluid. When you are go on supplying the heat, when you are go on increasing the temperature of this surface, what will happens, the temperature of the liquid is also go on increases. For a particular temperature, what will happens, the bubble formation will be takes place, means the bubbling at some parts. This is the complete one electrical heater surface, one small area. In that one, some few points, the bubbling will be bubbling of the water from the surface will be takes place. That one you're going to call as the nucleata. Okay. In some few surface, in a particular favorite places, the bubbling will be starts. That bubbling, the formation of bubbles, that one you're going to call as the nucleata. When once again go on increasing, see at point A, from here what will happen, the bubbles formation over the surface will be takes place in some fewer places. The bubbles formation will be takes place. When go on increasing the temperature, the bubble formation also go on increases. Here you can see that in the first case very few bubbles formation will be takes place from the surface, heater surface, but in after that one the bubble formation is also increases. Here you can see that when go on increasing, here this is the Q value, heat flux. The heat flux is go on also increasing. When you are increasing the temperature of the heater, means excess temperature go on increasing, at the same temperature, at the same time the heat flux is also go on increasing. This is the common thing. At particular point, the heat flux will be the maximum. This one you're going to call as the critical heat flux. When after this critical heat flux, when you are supplying the temperature, instead of increasing the Q value, the Q values go on decreasing here. Try to understand. After this point, from this point to this point, you're going to call as the nucleator boiling. In the nucleator boiling, what will happen? First, initially, some bubbles formation will be takes place. By go on increasing for a particular temperature, the more formation of bubble takes place, like that, like this. After once again increasing the excess temperature, instead of increasing the heat flux is go on reduces. The maximum heat flux is going to call as the critical heat flux. This is also going to call as the burnout point. Burn out, BRUNOUT, burn out point, means in sometimes this electrical heater maybe get burn out at that heat flux, but after that one you're going to call as the burnout point or critical heat flux or a maximum heat flux. After this the heat flux will be reduces even if you are increasing the temperature. The reason is that here you can see that the formation of bubbles covered over the surfaces, this will reduces the heat transfer. This will reduces the Q between what, the fluid as well as the surface, because of formation of this bubbles. This will what will happens, what the bubbles formation takes place or the slug formation takes place, that avoids the contact of water to the surfaces, that will be reduces. So that's why the heat flux will be reduces. This will be, this also go on reduces for a particular point. For a particular point means for this point the complete this heater surface is covered over the gas film, means bubbles will be completely surrounded over this heater. Here you can see that a complete film of boiling is covered over the surface. So this is the liquid. There is no contact between the liquid as well as the surface, because at that temperature, complete bubble formation will be takes place. Because of that one, this film separates the water as well as the surfaces. Because of that one, the heat flux is further reduced. That is the minimum heat flux in this condition. That one you're going to call as the Leidenfrost point, or a minimum heat flux, maximum heat flux, and a minimum heat flux. In the examination they may ask what is meant by the critical heat flux and Leidenfrost point. That time you have to write this sketch and you have to mention these 2 points. Okay. After this condition, after this point, further increase the temperature, further supply the current to the electric heater, what happens? Once again the heat flux is go on increases. From this point, what will happens? The radiation is coming to the picture. Means because of high temperature, the radiation heat will be moved through this film and heat the surfaces, heat the not surfaces, heat the water or heat the liquid. So once again the Q will be increases. So here these are the distinct zone. One is the free convection. In this one, what the surface is, electrical surfaces get heated, that heat is going to transfer to the liquid very near to the surfaces. After that one, for a particular points over the electrical surfaces, the bubble formation will be takes place. That one is going to call as the nucleata. When go on increasing the temperature, the formation of bubbles once again increases more, and also the heat flux reaches to the maximum condition. That one is going to the maximum heat flux condition. Complete this zone is going to call as the nucleata boiling. After further increasing the excess temperature, further increasing the temperature of the heater, instead of increasing the heat flux, that will be reduces, because the formation of bubble is more. What the formation bubbles is more, that avoids the direct contact between the liquid to the surfaces. So what will happen? Automatically the heat flux will be reduces. Here you can see that heat flux will be reduces, and they reach to the very minimum value at this point. That one is going to call as the Leidenfrost point. After this point, further increasing the excess temperature, the heat flux Q go on increases. See, the thermal conductivity of the liquid is high compared to the thermal conductivity of the gas, or a thermal conductivity of the empty place. Okay, because of this may be a bubbles or a film. Here the thermal conductivity is less compared to this one, so the heat transfer is automatically get reduces. So the Q will be reduces here. After this point, the Q reduces because the temperature is very high. In that condition, radiation is coming to the picture. The radiation doesn't require any media. Either it may be a liquid media or any media, or in the if it is there is no any media, then radiation heat transfer will be passed out. Those radiation heat transfer, the radiation heat that will be heat the liquid. Once again the heat flux is go on increases. This is the theory related to the pool boiling regime. This is asked in more times in the examination. The student must go through this one. Based on this one, we will solve one problem here. For this one here also, okay, based on the zones, you will get the problems. In some problems you will get the problems on only on the nucleata boiling. For this zone, from this to this zone, you have the separate equation. For particularly at this point, for this point you have a separate equation. And in the stable film and the radiation in the for this zone, this zone you have a separate equation. Totally 3 equations will be there. First one is in the nucleata boiling, and another equation on the critical heat flux, and another is on the stable film equation. Totally 3 different equations will be there. Different type of problems you will get. For those 3 different conditions, the equations I will show here. Just you go to the boiling condition. For the nucleata pool boiling, you should go for use this equation, the first one, nucleata pool boiling. For the critical or maximum heat flux condition, you go for this equation. For the stable film, this one, you should go for Hc Hr, and H is equals to Hc plus Hr. Okay, this equation you should be go for. Totally 3 equations. For the nucleata pool boiling, this one, maximum heat flux or a burnout point, this equation, and for the stable film boiling, this equation, you have to use this equation. Now we will solve the problems on these conditions. Take one problem. The bottom of a copper pan, 300 mm in dia is maintained at 140 degrees centigrade by an electric heater. Calculate the power required to boil water in this pan. What is the evaporation rate? That is the m that they are asking. Just I will write the sketch. A copper pan likewise, and the diameter is how much? 300 mm, and this electrical heater, the T wall or TS is 140 degrees centigrade, and this is exposed to the atmospheric. So this TV value, the vapor temperature, the boiling will be taking place by the atmospheric condition. So TV value is 100 degrees centigrade. Here TV values doesn't give, but you should know that one, this is the open pan, means the pan is exposed to the atmospheric condition. Anything at atmospheric condition, the water will be boiled at 100 degrees centigrade. That is the thing. So TV is equals to 100 degrees centigrade. The same data I have taken here. D is equals to 300 mm. TS is equals to surface is equals to 140 degrees centigrade. Water is exposed to the atmosphere, means the water is boiled at atmosphere is 100 degrees centigrade. Now the properties of the fluid you should be taken. That is, here it is clearly given that properties of the value should be take TW plus T sat by 2. TW plus T sat, saturation temperature, TW, okay, I will write TW, wall temperature, TW plus TV by 2, that is equals to 140 plus 100 divided by 2 is 120 degrees centigrade. Now we have to collect the properties of the fluid, that is the water, at 120 degrees centigrade. Okay, you should go for the contents for the liquid, and you should collect the properties at 120 degrees centigrade. You should collect all the properties. Here density and the kinematic viscosity is given. Product of this one, you go to the dynamic viscosity. Density multiplied by kinematic viscosity, that is equals to dynamic viscosity. At 120 degrees centigrade, you collect all the properties, and at the same time you have to find out density of the vapor. Density of the vapor, here you can see that properties of the vapor or steam, rho v, that is also is available. For that one you should go for the vapor. For the gaseous state, in the contents, for the liquids, this one. For the steam, go for the gases. 33, in page number 33, air is there, but we require is the steam. Here it is 100 and 120 is there. For 120, for 100 degree, the density of the vapor is 0.598. For 120, I taken as the 0.590. 590 I will take it. Just you should do here manipulation to get the 120 degrees centigrade. You just to take less than this value, or you can take 0.58 also. That is not a problem, because it's a very less value. If you're taking 0.598 or a 0.59, that doesn't make that much of difference in the answer. You can take 0.598 also, no problem, but I taken as the 0.590 kg per meter cube. Here I taken that value 0.59 kg per meter cube. Then HFG is the same thing, that is available in the data handbook, that is page number 144. In 144, HFG I taken for the 100 degrees centigrade as 2256.9, already explained. This is taken at page number 144, and this is taken page number 38. Okay, now come to the equation. Why I taken density of the liquid as well the density of the vapor, because those are the things that is in the equation. For the nucleator pool boiling, you have to take Q by A, means what? Heat flux. Rate of heat transfer per unit area is nothing but heat flux, that is equals to mu L, density of the liquid, HFG, latent heat of vaporization, G, density of the liquid minus density of the vapor. That's why I taken rho L, this is the rho L, and this is the rho V, density of the vapor. This one is taken in the liquid property. For the vapor I taken in the gases contents. In the contents page number contents, for the liquid property of water I taken, this is the rho L, this is the in the vapor, page number 38 and page number 21. These are the things taken in the remaining all the data. This is the mu L, rho L, CL, Prandtl number. Those are all the properties you take at the liquid condition. Only the density of the vapor is taken in the another page, that is page number 38, that is in the chapter gases. Sigma, okay, I'll leave that one. Rho L, rho V, CL, Prandtl number, and delta T is the difference between T sat minus TV. mean sorry, T surface are a T wall, TW minus T with delta T. Now you come to the new things. HFG is also already done in the condensation problem. HFG is what, 2256.9 kilojoule per kg at what, at 120 degrees centigrade, or 100 degrees centigrade. You take that much, doesn't make that much of a difference. Here sigma, CCF and N is the three different values you should be take. Here N is given. N is equals to 1 for water and 1.7 for the other liquids. Here in this problem, the liquid is what? Water. So N becomes what? 1. No problem. Next is what? Sigma and CSF. What is sigma here? Surface tension for liquid vapor interface. Refer page number 144 and 146. Now you have to calculate the sigma value, that is in the 144 and 146. Here it is the 144. Here it is given. Surface tension sigma of water against the air. Here water against its vapor. You have to take this one. Here for its vapor, above 100 degree is given, but here up to 100 degree is given, water with air. Here is about is given, almost the same data. Almost our value is how much? 120 is there. 120 is there. I take for the 100, very near to the value. Means 120 means what? The fluid properties at 120 degrees there. I will take at the 100 is equals to 0.59, or you have to do the interpolation 100 and 150 and do the interpolation. You will get this one. I already told that one. These are very less minute difference. You will get that one, so you won't get that much of difference. You, in the examination also, you directly take this value. That doesn't make that much of a big difference in the final answer. And for 100 degrees centigrade, sigma value is how much? 0.0589. Sigma value is 0.0589 I taken. Okay. Next is what in the equation? Sigma is over. Next CSF. See, remaining all the data is already taken. Mu L, rho L, CL, delta T, HFG, Prandtl number, everything is already taken. Rho V is taken from the other, taken from the contents, the chapter gases, and sigma and CSF. Sigma is just now taken, and the next is the CSF. CSF means what it is, that constant. CSF is the constant. See table in the page number 143. Page number 143. Here you can see in the 143. Here the liquid is what? In our case, liquid is the water, and the heating surface is what? Copper. See, liquid is water and the heating surface is copper. Suppose if it is the platinum or another things, the value will be the difference. Platinum is water, copper, water, platinum, water, brass, water, other things will be there. Embry, polished copper. You take water and copper. For the water and copper, you see what is the value? CSF 0.013. Take that value. Here I taken that value here. CSF is equals to 0.013 is taken from the page number 143 and 146. N is equals to 1 for the water. Now all the data is taken. Now you substitute to this equation. The equation what is there? You substitute to this equation. All the data is there. After substituting all the data, I obtained as the this much value, 13.46 10 to the power 6 watt per meter square. Okay, in this problem what they ask, you have to find out what? M dot. Next, already I explained that to calculate M dot you require a Q, because Q is equals to what? M dot into HFG. Now you found out that what? Q by area. Just now you find out Q by area, that is equals to Q. You have to calculate Q. That is how to calculate Q? Q is equals to small letter q into A, means heat flux into area. Q into area. Area is what? Pi d square by 4. You obtain Q value is this much, 948.48 into 10 to the power of 3 watt. Q is equals to M dot into HFG. HFG is already be taken, that is 2256.9 into 10 to the power of 3. Substitute here, find out the M dot value. Here also, while substituting HFG, very important point is what? You don't forget multiplication of 10 to the power of 3. Okay, because this is in the kilojoule, HFG is in the kilojoule per kg. Kilo means what? 10 to the power of 3. Don't forget. If you forget this one, complete value will be going to be wrong in the examination point of view, in the examination also. Okay, now just now we solve the problems on the in the nucleator pool boiling condition, means in this zone nucleator pool boiling, this condition. And then the same way, in the you can calculate the maximum heat flux also you can calculate the stable film condition also. Here you can ask, sir, you here in the textbook it is given Ts minus Tsat up to it is the 30 degrees centigrade, but here the difference you are getting is the how much T wall minus TV you're getting a 40 degrees centigrade. But some problems data may be varies, but don't get confused. What the data is given in the what the data is given in the problem, you just take those data to calculate the terms, calculate the unknown things. Here calculate the power required to boil the water in this pan. What is the evaporation rate? Means you have to calculate the Q as well as what? This is the power and m dot is the this thing. Both are the things we calculated. Now did the problem on this one. In the same way you can solve the problem on the maximum heat flux as well as this one. Just I will brief out through this worked example problems only. Okay, here is the one problem. A nickel wire of 1 mm diameter and 40 mm long carrying a current is submerged in a water bath open to atmospheric air. Calculate the voltage at the burnout point. Calculate the voltage at the burnout point. It is mod. You have to calculate Q max. If this at point the wire carries the current of 190 amps. Okay, Q is equals to voltage into amps. You have to calculate the voltage. V you have to be calculate. I is given. Once you calculate the Q, okay, once you calculate the Q, voltage you can be calculate. See, just I will brief out here. In this problem, what they asking? You have to find out what is the V. Here the condition what? Q max. So you have to calculate Q. Once you calculated Q, the voltage is what? Q is equals to V into I. Then V is equals to Q by I. I is given, 190 amps is given. This is the maximum heat flux condition. Just you note down the things. P is equals to 1 atmospheric. For 1 atmospheric temperature, saturation temperature or a vapor temperature is 100 degrees centigrade. In the same way, you collect the properties of water. Collect all the properties of water. What I shown in the page number 21. Page number 21 means here at 100 degrees centigrade only they taken. Okay, here the surface temperature is okay. In the burnout point, the wall temperature and surface temperature is not required, but is not given here. But here it is given that water will be boils at atmospheric, means wall temperature, so vapor temperature becomes 100 degrees centigrade. At 100 degrees centigrade, you collect the properties from the page number 21, that is density of the liquid, Prandtl number, all the values, and properties of the vapor, that is also at 1 atmosphere at 100 degrees centigrade, that is page number 38. Rho V should be calculated here. After calculating all the terms, after taking all the data, you substitute here 0.18 HFG rho V into this one. After this one, you will get the values like that. You will get Q by area answer. This is what heat flux, but we required is what? Q is equals to Q into area. Area means what? Pi into D into L, pi dl. Pi dl is already given. Diameter is 1 mm, length is 400 mm. Substitute here. Find out AS. then you obtain the Q. After obtaining the Q, next is the V into I. V into I, find out the V. See here in this data, and in this book the taken is the 0.149, but here in the data handbook it is in the 0.18. Means this is almost equal to what? 0.15. This is 0.18. So the equation will be varies from one textbook to the another textbook, very slightly, very lightly. Equation will be varies, don't get confused, but the procedure is the same thing. Collecting the data, everything is the same thing, but what the equation will be there in the data handbook, use those equation, that's all. Now just we solve the problems on the nucleator pool boiling and maximum heat flux condition. How to solve this problem I also explained. The rho L, rho V, rho V square, the sigma, you know it, how to take the, okay, sigma I will explain once again. Sigma is what here? Sigma, page number 144. At 100 degrees centigrade, 0.0588. 0.0588. Okay, these are the for each standard books they having a separate one separate data handbook, so you don't get compare these values with this data handbook. Some minute difference will be there. Always use this one, but the procedure and taking the data equation follow the some standard textbook, but you should use the datas only, this data handbook only. Okay, this is the one good textbook, that is the Mahesh M. Rathore. In the notes also I given the reference. If you got this textbook, refer this one. I commonly, my most preferably I refer this textbook only, Mahesh M. Rathore heat transfer textbook. Okay, this is the problems on what? Critical maximum heat flux. Like that you should go for the stable film condition also. In the problem, if it is emissivity is given, see in the problem if they ask find out the if the emissivity is given, that is nothing but the problem is on the film condition. Suppose in the problem it is ask find out the heat flux at the burnout point or maximum heat flux condition, then you go for this condition. Suppose if it is a find out m dot or nucleator boiling, then you go for this equation. You go for this equation. Okay, now we solved all the problems. The students must go through the different textbooks and try to solve the different problems. Suppose if you are having any difficulty, any doubt is there, you can contact at any time, and by WhatsApp or by email. Thank you.